So today we're going to continue talking about physics of music. We kind of laid the groundwork for this yesterday. Today we're just going to expand and elaborate on a lot of these things. So for today's plan, we're going to recap the similarities and differences between fixed end harmonics, which is like string instruments, open end air columns, that's where both ends of the air columns were open, of course, and closed end air columns. That's when one end of an air column was closed and the other end of an air column was open. We're going to do a couple sample problems and hopefully we're going to have lots of practice time today. I do have a homework assignment I'll be giving out at the end of class today, so we will want to use that time effectively. So for fixed end harmonics, such as in stringed instruments, I want you to remember that the ends are what we call nodes. So when you have your standing wave and it's appearing to just bounce up and down, the end points on that standing wave are called nodes because they are points that don't appear to move. Now with fixed end harmonics, the number of antinodes, those are the peak points that go up and down, that actually tells you the harmonic number of that fixed end harmonic. Now I don't want you to get too used to the idea that the antinodes is your harmonic number. It really only works with fixed end harmonics. It's a bit of an oversimplification, so I wouldn't get too used to it, but it is just a useful thing to remember for fixed end harmonics because it allows you to identify for a fixed end harmonic what the harmonic number is just by looking at it. Now, last class I introduced this really massive, scary looking formula, but I'm going to kind of like ease your worries today, and I will remind you that this equation that you see on the top in the center of the page here is actually going to be given to you on your unit exam, right? So with string waves, those are the ones that have fixed ends, the frequency of that wave depends on the mass, the tension, that's how much force is stored in it, and the length of that string. So T again represents the tensional force. Don't confuse it with T that we did earlier on in oscillatory motion, which was the period, right? In this case, the capital T we're using is actually the tensional force. So your frequency for a harmonic number of n is equal to n times the square root of TL over m divided by 2L. So again, I want to remind you, the n that you see here is your harmonic number. So if it was the first harmonic, n would be 1. If it was the second harmonic, n would be 2. T, of course, is the tensional force stored in that string. So in other words, how tight is it? So if this was on a guitar, for instance, the tighter you tighten the strings on the guitar, the higher the tensional force. L is, of course, the length of that string, and M is the mass of that string as well. Now, this is very similar. As a matter of fact, it's actually equal to the formula we set up to predict what the frequency is of a fixed end harmonic, which was N times V over 2L. From this, since N and 2L are staying put, we can therefore determine that V, the velocity of the wave going through a fixed end harmonic, or a fixed end string, sorry, is equal to the square root of TL over M. That piece down here is not going to be given to you on your unit exam, but this equation will be. But since we are already expected to remember that for fixed end harmonics, your frequency is NV over 2L, this shouldn't be too much more of a stretch to just say that V is equal to this square root piece right here. So the second type of harmonic we looked at were open air columns, right? So this is where you have some sort of open-ended tube where there is no closure on both ends. What the good news is with these kinds of questions are they're very similar to fixed end strings. The main difference, however, is that the endpoints, instead of being nodes, are actually antinodes. But the nice thing about this is the formulas for both of these are still the same. Your frequency for any n harmonic is the exact same formula. And likewise, if you were to rearrange this, you could actually figure out that your wavelength is just 2L over n, because this Fn formula is just an extension of your universal wave equation, V equals frequency times wavelength. Now I want you to note that each successive harmonic is just a multiplication of the frequency of the fundamental, right? So in other words, this n is the only thing that affects the difference between the first harmonic, the second harmonic, the third harmonic, and so on. Now for closed air columns, these are actually a much different case. These ones have an antinode at the open end, and a node at the closed end. Now, because of this difference, they actually have a different set of formulas as well, and you will be expected to memorize this as well. The frequency for any n harmonic on a closed air column is NV over 4L instead of 2L. Just a minor change, it's not a big change, but you still have to realize that for closed air columns where there's one closed end, it is actually going to be the same. Now I'll also remind you, this picture that I put in here, I don't particularly like it because whoever put it together actually put it together incorrectly. The first one and the last one are correct. That is the first harmonic and the fifth harmonic. But this one isn't actually the second harmonic like it says, it's actually the third harmonic. And I want you to remember that for closed air columns, you can only have odd harmonics. So it's not actually possible for you to be putting in an even number for n into these equations. Now again, for these closed air columns, if you were to double or quadruple or etc. the fundamental frequency, it would actually be impossible. The reason being is you have a node at your closed end, so if you were to double the length, double the frequency rather of that harmonic, you would end up having a node at both ends. And as we know, we can't have a node at the open end, it has to be an antinode. So this is why only odd harmonics occur in closed air columns, because again, we want to make sure that we have a node at the closed end and an antinode at the open end. All right, so we're going to run through a couple examples here, and hopefully this will alleviate any stress you might be having about these kinds of questions. The first one is saying we're going to suppose we have a 90 centimeter long string with a mass of 2.2 grams, and it was tightened to a tensional force of 15 newtons. We want to find the speed of the wave moving through that string. Now, before we even begin, we should always do what we've always done in Physics 20 and change our units to common units that we always like to use. We don't like using centimeters. So before I even begin here, I'm going to change this 90 centimeters to 0.90 meters. And likewise, grams aren't exactly what we want to use. So we should divide this by 1,000 to turn this into 0.0022 kilograms. Now, 15 newtons, of course, newtons is the standard unit for force, so that one's fine. We're going to start here by finding the speed of the wave moving through the string. Now, to be fair, on a question like this, you will be given the formula for a fundamental frequency, which again looks like Fn equals n times the square root of TL over m divided by 2L. Now, remember that this square root piece up here is technically equal to the velocity of the wave going through the string. That's explicitly what we're looking for in this question. We don't need this entire jumbo formula here. We just need that square root piece. So I can start by saying V is going to equal the square root of TL over m. And then we can actually just plug all of our numbers that we already have in. We know T, that's the tensional force. It's going to be 15. So I'm going to say this is equal to the square root of 15 times by L, which is the length of the string. And again, that's 0.90. And we're going to divide that by the mass of the string, which is 0.0022. Throwing this in your calculator, and you're just going to have to give me a second to do this. 15 times 0.90, divide that by 0.0022, and then square root that answer. You're going to find that your velocity to just 2 sig digs, because that's all we have in the question, is 78 meters per second. Now the next part of the question is saying, what is the fundamental frequency of the sound produced? Well, the fundamental frequency is a fancy way of saying the first harmonic, or in other words, this is where n equals 1. So this is where we're going to use this really big formula up here. I guess some good news is we don't have to plug in the entire square root piece, because in this last question, we were actually able to figure out that big square root piece there. So we don't actually need to worry about, plugging even more numbers in there than needed. So really what I'll say is we know our frequency for our first harmonic, so we'll call it F1, is going to equal 1 times by that whole jumbled square root mess, which we calculated in the last question to be 78. Just by the way, just for good measure, I'm sorry, I'll just kind of cut this off here. I'd actually be a little bit more comfortable if I use my decimals in this. And I know I didn't say it here in the video, but I actually kept it here on my calculator. I'll use as many decimals as I feel comfortable with, just because I don't want to lose any of these numbers in the whole translation. So instead of just 78, I'm going to put that as the more honest 78.3349. And I think that will be a comfortable enough amount of decimals to use in this question. Anyway, now we'll divide that by 2 times L. L was also given to us in the question. It was 0.90, so this will be 2 times 0.90. And we'll throw that in our calculator once again as well. So 78.3349 divided by 2 times 0.90. This is actually giving me a fundamental frequency to just 2 sigdigs of 44 hertz. So in this question, really, it was just a matter of realizing we had a fixed end because it's a string. Therefore, our fixed end formula is going to apply. And we just have to realize what information was given to us in the question and how we can tie it all together to find what we're looking for. Okay, so this next example is going to be a little bit trickier. We're again dealing with a string that when plucked is going to produce a fourth harmonic of 200 hertz. The question's asking, what would the third harmonic of that string be? Let's first deal with as simple of a harmonic formula as we can get. Since it's a string, we know our nth frequency, so our harmonic frequency, is going to be equal to NV over 2L. But unfortunately in this question, the only information we were given was that it was a fourth harmonic, so N is 4. And, oh, that's not a very good 4. N is 4, that's a little better. And that the frequency was 200 hertz. Well, let's start there. We'll say that 200 equals 4V over 2L. Now, because we have 2 missing variables here, the V and the L, there's no way we're going to be able to solve this. But if I somehow were to change this just to a V over 2L, that would actually tell us what our first harmonic would be. And then remember that any successive harmonic is just a multiple of that first harmonic. Well, notice if I just divide both sides by 4, that'll cut the 4 out of here. Dividing by 4 on the left side is going to knock it down to 50. So 50 would equal 1V over 2L. Now, 1V over 2L, by looking back at the original formula, that would be our fundamental frequency of our first harmonic. So our first harmonic is only 50 hertz. Now, I know the question is asking, what would the third harmonic be? But I guess the third harmonic would just be 3 times this because it is a multiple of that first harmonic. In other words, if you wanted to ignore this one here and say V over 2L, just this part right here, is equal to 50, that means when you look at your third harmonic, F3, you could say it's going to be 3 times V over 2L, which we already determined was 50. Long story short, no matter how you think of this, we're going to see that our third harmonic frequency is going to be 150 hertz. And we do want our answer to 3 sigdigs because that was what was given in the question. So 150 hertz is a perfect final answer. Now for our last example here, given that the speed of sound at room temperature is about 340 meters per second, find the height of an empty glass needed to produce a sound with a fundamental frequency of 150 hertz when air passes over the opening. So if we have an empty glass, first of all, we know the bottom of the glass is going to be a closed end, and the top of the glass is going to be an open end. It even refers to the opening of this glass, right? Therefore, this is what we call a closed end system. Now, closed end are the tricky ones because they actually have a different formula than the open end systems, which would be the same as a fixed end system. So a closed end system, again, has a frequency for their harmonics, n being the harmonic number, of NV over 4L instead of 2L. So it's not a lot different, it's just a slightly different formula. Now in this question, it told us we had a fundamental frequency of 150 hertz. Remember, a fundamental frequency is a fancy way of saying your first harmonic, so n is equal to 1. We know what our velocity is, it's 340 meters per second. What we're trying to do is we're trying to find the height of that, so in other words, the length of this glass, in order to produce that sound. So we know our frequency, we know our velocity, and we're looking for length. This question is just a matter of using a little bit of algebra, so even though it might have seemed a little bulky at first, it's just a matter of plugging in the numbers that we already have into the equations that we already know. Now, I know this equation is not given to you, but just like the open-end one and just like the fixed-end one, you're just going to have to memorize it, okay? Anyway, so for Fn, we already know the Fn is 150. This is going to equal NV, so N is 1 times V is 340. That's a 4, 340, divided by 4 times L, and L is what we're looking for here. Personally, I think the best way of going about this would be to multiply by 4L on both sides. If you multiply by 4L on both sides, 150 times 4L is 600L, and that's going to equal 1 times 340, which is, of course, just 340. And we want to get L all by itself, so let's divide by 600 on both sides. So 340 divided by 600 is going to give us L. And again, with L, we're only going to want 3 sig digs, judging by our question, because we had 3 sig digs here and 3 sig digs here. So for 3 sig digs, I'm going to round this to 0.567. And since that's a length, that's going to be measured in meters. So the length of this glass, pretty tall glass by the looks of it, it's going to have to be 0.567 meters, or if you prefer, you could call that 56.7 centimeters. Either one of those answers are totally acceptable. So for practice, I want you to continue working on the string and air columns worksheet. I did hand that out last class. There should be extras on the front table if you need them. But other than that, there's a new homework assignment that's going to need to be handed out. It's the oscillatory motion homework assignment. This is going to be due on Tuesday next week. So you will have some time today, of course, as well as some time tomorrow and Monday, as well as obviously the entire weekend to get that done.